Hey everyone, and welcome to this explainer. Today, we're extracting some incredible, highly practical insights straight from the Math Refresher workbook for adults returning to school. We're going to dive right into the finance section to demystify something that affects every single one of us, personal finance. Specifically, we're looking at the math behind how money grows or, how debt snowballs. It's a fundamental concept you absolutely need in your toolkit.
Okay, let's dive into this. I want you to ask yourself a highly relatable question. If you left money in the bank today, what would it actually look like in 15 years? Would it just sit there gathering dust? Would it grow a little bit? Well, the answer entirely depends on the mathematical engine powering that account, and that exact engine is what we're going to decode right now.
Section 1. What is compound interest?
So the workbook defines compound interest as interest calculated on the initial principal and also on the accumulated interest from previous periods. I really want you to focus on that second part. It's not just some flat rate on your original deposit. It's literally interest building on top of interest. Your money makes money, and then that new money starts making its own money. It's like a snowball rolling down a hill.
Now, what's really interesting about this slide is how it compares to simple interest. Simple interest is based only on the original amount you put in. Say you put in $100 at 5% for 2 years, you get $110. But with compound interest, because you earn interest on your previous interest, that exact same $100 at 5% for 2 years becomes $110.25. Now, I know an extra 25 cents doesn't sound like a real game changer, but as the workbook points out, compound interest is a bit trickier, and it consistently yields a higher result. As we'll see in a minute, when you scale this up over time, that tiny difference turns into an absolute mountain.
Moving on to Section 2, breaking down the formula. Don't worry, we're going to make this totally intuitive.
Here's the actual formula straight from the text. It looks like a giant puzzle, but it's really not. Step 1 is just identifying our variables. P is our starting principal, the amount you start with. R is the annual rate, and N is the number of years. In Step 2, we just plug those values right into the formula. So for our $100, we pop that in for P, 0.05 for R, and 2 for the years. And in Step 3, we calculate the final amount. We see our original $100 grew to $110.25. See? It's really just a matter of plugging the right numbers into the right places.
All right, Section 3, growing $10,000. Let's really scale things up. And this brilliantly illustrates what happens when you give compound interest a little bit of time and a slightly higher balance. The workbook gives us a great example of a $10,000 initial investment at an 8% annual compound interest rate. Just look at this growth. By year 5, you've got over $14,600. By year 10, it jumps to over $21,000, and by year 15, no way. That original $10,000 has grown to $31,721.69. The money has literally more than tripled just by sitting there and compounding year after year.
But it's not all sunshine and rainbows. Section 4, the cost of borrowing. $29,160. I really want you to let that number sink in for a second. The workbook presents this scenario where you borrow $25,000 to buy a car at an 8% interest rate, compounded annually. If you make absolutely zero payments for the first 2 years, this is what you owe. That original $25K has exploded into $29,160. That is over $4,000 in interest alone, generated in just 24 months. Why? Because the interest was piling on top of the interest you already owed. It's a really powerful reminder of how debt can just totally spiral if it's left unchecked.
Okay, Section 5, reverse engineering your rate. This is where you get to play detective.
So, the crucial point is that this math works in reverse too. The workbook gives a really cool example. Let's say you have $1,210 after 2 years from an initial deposit of $1,000. What was the rate? Well, Step 1, we set up our equation with our end goal and starting amount. Step 2, we divide to isolate the rate multiplier. Step 3, we take the square root to strip away the time factor. And finally, Step 4, we solve for R to reveal a 0.1, which is exactly a 10% interest rate. Just like that, you've reverse engineered the bank's returns. Pretty cool, right?
By understanding the simple math behind these transactions, you really unlock the ability to manage your financial future. Whether it's choosing the right savings account or understanding the true cost of a car loan, the formula is always the exact same. So as we wrap up this explainer, I want to leave you with one final, absolutely vital question based on what we've learned today. Is your money compounding for you or against you? Take a look at your own finances and run the numbers. Thank you so much for joining me today, and keep learning.